section in chapter 9 is correlation. Have we heard of this word, correlation? Well, what do you need in order to have a relation? Two, that's the number 2.
2 types of data.
Okay, 2 things. Matthew.
Not like mathematical events, but let's say like something raining, you remember it happened.
Exactly. So we have 2 of something, events, variables, data. Doesn't matter. But we need X and Y. I always say it is only when you have an X you start wondering why. In Jared's case, he'll probably cry.
I do that every night.
I knew something was coming, so that's why I said something about you. So X, Y hard data in the sense for every value of X, you have a corresponding Y value. And there is some sort of an association between the 2. In mathematics or algebra, we have Y equals f of X. And X has a name. What variable is X? Independent variable. Y is the dependence variable. And what is that f? What does it stand for? Function. So when I read this, I read it as y is a function of x. What does it mean if y is a function of x?
Y depends on X.
It means y depends on x. In other words, y changes in some way defined by this function. The function defines how y is going to change with respect to x. What is the simplest function that you know? What?
Y equals X.
0.
Y equals X.
Y equals x. What type of function is that?
Linear.
Linear function. Now, had Graham said y equals 0, that would be correct. Because y equals 0 is a horizontal line, and it is in fact a function. Nick said y equals x, that is also a function. So just to refresh your memory, if x is 1, what is y? 2, 8, it's simple. So clearly y changes as you change the value of x. So that is the mathematical case. What do we do in statistics? Well, math perspective. I'd call this as the objective of statistics. Same thing. Why? Instead of calling it a dependent variable, sometimes, or in most cases, we call it a response. Instead of an independent variable, we call it a predictor variable. Now, where does the terminology come from? Well, response, we are trying to see or measure some sort of a response defined by some predictor. For example, height could be a response, weight would be a predictor. F in statistics is unknown. So f is an unknown function that I'm going to estimate using the data. We learned about mathematics so that you can apply to other fields. The concept of functions was taught to you in algebra, just in case if you went to stats, you know what the functions are. So we have a whole lot of functions, and our goal is to estimate one of those functions. And I can't just run through every single function in mathematics. Even if I wanted to do that, I'll probably be dead by then. So there has to be a way for me to gauge what function to use even before I go and play with the data. To do that, we use something called a scatter plot. Have we seen a scatter plot before? Yes, hopefully. As I mentioned earlier, we need XY powered data. So mind you, these are random data points. Unlike mathematics, where you have, a line, set of points that lie on the line, these are random values because let's say if x is not likely true, but so let's say x is the amount spent on lunch and y is the amount spent on dinner. If I measure this observation from, say, Rebecca, an x value, I have to go and measure a y value from Rebecca, correct? Because they are related. I can't measure x value from Rebecca and connect it to y value from Hannah, which is why we call it paired data. And these are random observations, but if you look at that plot, do you see an underlying pattern?
Yeah, the line of best fit just
Yes, we'll get to that, my young Padawan learner, but before that.
Yeah, there's a positive trend going up and down.
Is there a trend or not? Yes, there is a trend. If so, what type of trend? Quadratic? Okay, Matthew, is it quadratic?
No, it looks to be linear. Well, line of best fit would definitely be closer to linear.
It looks like linear to me. Do you agree? Kind of. So I look at data of this sort, it immediately will tell me that I have to use a linear function. In other words, the unknown function is defined by the equation of a line, which is done it?
Linear, I don't know.
The equation of line.
Y equals mx plus b.
Y equals mx plus b. So I look at this picture, I recognize a linear pattern. So I would go for y equals mx plus b. Still, I do not know the values of m and b. That's why I call it unknown. And I can estimate the values of m and b using the data. That makes sense. Suppose I have another data set. Looks something like that. Still random. What does it look like?
Like a negative linear.
It still sort of looks like a line, correct? So probably something like that there, something like that. So both of those are linear. Okay. So each of those dots is a point, and what type of a pattern do you see?
Sine, cosine.
Sine, cosine, so definitely not linear. Do you agree? So something like that, and that is what we call nonlinear.
Everything.
Everything. Is there a relationship? No. Think about it this way. Think about interpersonal relationship. Maybe between friends, spouses, girlfriend, boyfriend, girlfriend, doesn't matter. Now, what would you say about this relationship? Over time, this is sort of the trend that you see. So is that positive or negative? Positive. Things are going up. Looking great. So this is positive. How about that? Clearly not looking great, so negative. Is there a relationship? Absolutely. But to run away from that relationship, it's a roller coaster, right? So there is a relationship, but it is just not linear. So when it comes to linear relationships, we can call it positive or negative or even constant. Nonlinear relationships, we can identify the underlying pattern, but it is inappropriate to say positive, non-linearly correlated, or negative, and so forth, because things can go up and down. Here, no relationship whatsoever. No matter how many days you go together, it's not going to work. Give up. Are we clear? Yes.
So that was the top one's nonlinear because obviously it's not bottom one, you just wouldn't even call it that because it's so random.
Exactly, it's pure, it's completely random. So step one, I visualize it using a scatter plot. I identify linear, non-linear, no relationship. If I encounter something like this, I just give up. But the others, there is some meaning. I'll try to find out from data. So if you want to assess the strength of a linear relationship, would we consider both of them to be linear? Yes, but which one is stronger?
Left.
One on the left. Why is that, Joy? What gave it away?
Because the dots are closer together.
Dots are closer together, okay? In terms of statistics, if observations are very close to each other, then less
What's that one?
Versus-
Go ahead.
Less variable.
Less variation, the variability is small. In other words, it's quite consistent. So the strength of correlation is directly related to the variation that we observe. So lot of variation, not a lot of variation. Of the two, this one would have a stronger positive correlation compared to that one. In a similar manner, if I drew something like that in a different direction, that would have a stronger negative correlation compared to that one. But one would want to quantify numerically as to what the correlation will be. To get that numerical value, we use something called a linear correlation coefficient. If you look in the textbook, there is a really huge formula which you have to use to find the value of the linear correlation coefficient. But what are we going to do? Use the calculator. I'll show you how. So this is denoted by the letter R. And the value of linear correlation coefficient is always between -1 and 1. Of course, it can equal to 1 or -1, but that's not a case that we would encounter in statistics because there will be no randomness at all. If the value of R is very close to 1, strongly positive correlation. If it is closer to -1, strongly negative correlation. So seems rather objective. Well, what does strongly mean? Typically 0.8 and above would be strong. I've seen articles where people claim correlation is strong when it's like 0.52. Right, that's not strong correlation at all. So it has to be close to 1, maybe about 0.85. In a similar manner, if it's about negative 0.85, that would be negative correlation. What if we are close to 0?
No correlation.
No correlation. By close, I mean really close to 0. So, do we expect the value of R to be positive or negative?
Zero. Zero.
This one,
Oh, that's positive.
positive. That one,
Negative.
All
Positive.
maybe positive.
okay,
All of
No.
those.
nothing. So here, R is probably close to 0. There, R definitely is less than 0, negative. There, R is going to be greater than 0, positive. And of these two, which one's going to have a higher R value? The one on the left, because this has a stronger correlation compared to that. So the value of R here would be greater than the value of R there. What did you guys say for this one?
Zero.
0,
Over the top one. Positive.
positive. Well, if you look at the positive side of things, it's positive. Negative side of things, negative. Put them together, really doesn't matter. But you're missing an important point about R. R stands for linear correlation coefficient. If you use the formula and computed a value of R for this data set, you will get a number. It could be positive, it could be negative, but it would be inappropriate to use that value of R to make any sort of inference, because the value of R can only be used to infer linearly correlated data. Does that make sense?
So you just wouldn't use it, or you classify it as zero like you did the bottom,
I wouldn't even look at the value of R.
but then why would you look at the R is zero because it's
It tells me that there is no relation. It's actually a good question. Why would you even look at this? What I'm trying to say is, if you have nonlinear data, you will get a number. For example, this seems pretty nice. It could produce a value of 0.85. But I can't say the correlation is strong because the value of R is 0.85. The reason being the data is nonlinear.